We can now also look at the band edges that we obtain. So here in the solid line are two experimental data sets where people have measured the band gap of aluminum gallium arsenide as a function of aluminum concentration. And in the previous lectures I mentioned that gallium arsenide is direct and has an X point that is up in energy, and that aluminum arsenide is indirect, it has its minimum at X, and its gamma point is way up in energy. And at some point they cross, and that crossing point is roughly at 40%. That means in RTD-like devices, people only go ever up in aluminum concentration up to 40%, because going up any higher doesn't really increase your gap anymore that is being seen. So there's a crossover. If we now do our random alloy calculation, we basically overlap this reasonably nicely. If we did this in a virtual crystal approximation, where we just average the material properties, at gamma we would be very wrong. So here we really would be getting the wrong trend in virtual crystal approximations, which is really where we want to work in less than 40%. Okay? So now, if we do a supercell calculation, we can basically overlap experiment very nicely. If we did this virtual crystal approximation, we don't get the gap quite right. The gap is too large. And we can now also compute these fluctuations due to aluminum placements. That would be configuration noise. Configuration noise would be taking this exact same concentration, say in a cell of 200 atoms, and you say you want to have a 0.2 aluminum concentration. That means you have to have 20 aluminum atoms and 80 gallium atoms. And you always choose 20 and 80. But you randomly distribute them, but exactly 20 and 80. That would be configuration noise, right? Because you configure the atoms slightly differently. But in reality, when you grow this stuff, chances are you're not going to hit exactly 20 and 80. Right? There will be a statistical fluctuation around that. That would be concentration noise, because the concentration would have noise on it. And we're going to start looking at the differences between those now. There's a third one, which could be position noise. And why would that be? Here, and this is not relevant in aluminum gallium arsenide. In aluminum arsenide and gallium arsenide are virtually on exactly the same strain, lattice constant, right? So there is no strain. So the atoms wouldn't move out of place due to strain. So they don't have noise on their positions. But in indium gallium arsenide, the lattice constants are rather different. They would actually move out of place. So you would have positional noise as well. Okay? So let's move through that and ask ourselves, how important are these fluctuations and how do they depend on system size? So here, what I've done is calculated 3,000 atom systems, 2,800 samples, and we started to look at the configuration noise only. So we locked in place 20% of aluminum and have a sigma of 0 in that concentration. And we find a nicely homogeneous distribution of histogram of conduction band edges. Okay? For each sample, we bin them up and get a histogram and find a nice band gap of roughly 0.56. And it looks symmetric in the conduction band. The valence band has a slight slant to it, and it's not perfectly symmetric. And if I now look at the difference for each sample in the conduction and the valence band, and here I have a gap. So here I have a statistical fluctuation around the gap. So now you can see that the noise of 0.7 and 0.5 don't quite add. Okay, so the width of this curve in the middle and the width of this curve on on the left don't quite add to the width of that curve on the right. So that is sort of an indication that the two are not correlated. Okay? And if you plot it in these dots here, for each of these 3,000 samples, so you see 3,000 dots here, you plotted the valence band edge and the conduction band edge, you get a round distribution. Right? That means they're not correlated. You couldn't lay a straight line through this here anywhere where you say, okay, if the conduction band goes down, the valence band goes up, or something like that. There's no rule. Okay? So it looks like the configuration noise is uncorrelated. But now we can do the next experiment where you say, we can, instead of having a delta function at exactly 0.2 of the concentration, we can allow it to have some fluctuation. We just roll the dice. We'd like to aim for 0.2, but we roll the dice. And for 3,000 atoms or so, you get a certain distribution, and that sigma is 0.011. So it's not significant, right? So we aim for 0.2, and we get somewhere between 0.21 and 0.19. Right? It's not a tremendously large distribution. And what we get is now a distribution of valence bands and conduction bands and gaps that is much, much broader than the distribution we had here. So the blue lines, the blue histograms from the top row are now translated into the middle row here in the blue, and in red we now have this concentration noise in there as well. Okay? So if you're not having tight control on the concentration and the exact number of atoms that you have, so not exactly 20 atoms and 80 atoms of aluminum and gallium, and you can lock that into place to be 20%, you will have noise, right? You will have 19 and 81 or whatever, right? If that's the case, your bulk band edge is going to have a bigger fluctuation.